Hi everyone, welcome to the General Physics 2 lecture on current and resistance, the first lecture in our unit on electric circuits. To try to place this all in the storyline of where we've gone so far, we started our electrostatics unit by talking about what is electric charge and what it means for an object to become electrically charged. We then explored the different ways you can characterize two or more charges that are in a system. You can talk about the force that those charges exert on each other, or you can talk about the amount of electric potential energy that's stored in a system of charges. Then we threw some kind of abstract curveballs your way. We talked about if you have a single charge, you can characterize the area around that single charge either by the electric field that exists in that area, and then if you put another charged object in that electric field, it will feel a force. Or you can talk about the electric potential surrounding a charge. And if you put another charge at a region where there's a certain value of electric potential, it gives you a quick way to calculate how much energy is in that system. Now, as we transition into electric circuits, the big kind of question that we're taking on is what happens when we take these charges, put them in a conducting material, and get them to move in a systematic way? How can we use that to do stuff, to make things happen? Well, in order to understand that, we have to understand two concepts, the concept of electric current and the concept of resistance to the flow of that current. So, what I'm going to do in this lecture is put in a series of conceptual questions and encourage you to, if you don't already have an answer in mind by the time I get to the end of reading the options to that question, pause the video and see if you can figure out what the answer is before you hear what my answer to a particular question is. So let's start this by something that we actually saw at the end of the electrostatics unit. That is this system of a parallel plate capacitor. Two conducting materials that are separated by some distance, and typically we talk about the capacitor in the context of being charged. So if I charge this capacitor and make one plate positive and the other plate negative, there exists an electric potential difference between them. We could call that delta V. So the question is, what mechanism could charge the plates in this way? Is it that negative charge was transferred from the left plate to the right plate, that positive charge was transferred from the right plate to the left plate? Do both 1 and 2 work, or is it neither 1 or 2 and some other mechanism? This is actually a question where I can make a good argument that at least 3 of these options could be considered to be correct. So therefore, I'm not going to put this question on an exam. The most obvious answer is that in our structure of matter, our model of matter, the positive charge is the protons that are bound in the nucleus of an atom, and the negative charge is the electrons that are surrounding that nucleus. In that context, only the negative charges are the ones that we can move in these systems that we're talking about, the electrons. So you can make an answer that A is the correct answer here, right? I had to take some electrons off the positive plate through some process, put them over on the negative plate, and that made the right-hand plate net negative, but stripping those electrons off the left-hand plate left that plate with more protons than electrons, so it was overall positive. But there are a lot of people that do this stuff and think about this stuff with having both positive and negative charge move. And one way you'll hear this framed is in the concept of holes. So a hole is an absence of an electron. And if you think about a neutral atom and then you pull an electron off of it, you now have a place where there used to be an electron. Now there are more protons in that atom than there are electrons. So that atom is net positive. Well, if you put a whole line of atoms in a row, if an electron hops from atom to atom, it turns out that the absence of an electron, that electron hole, moves the opposite direction. And in fact, this can be helpful in thinking about how we think about electric current, since by convention, electric current, we're going to say, is going from positive to negative. So that's a long-winded way of saying you could make a good argument that C is a correct answer here, that both positive and negative charge move, and if that's your model, perfectly fine for what we're going to do here. Also, you could actually charge this capacitor without taking negative charges off the one plate and putting them on the other, or positive on the other. You could independently take two conducting plates, right? Charge your rubber rod and rub it on the plate that becomes negative. Charge your glass rod and rub it on the plate that becomes positive, and you would have a capacitor that would function in much the same way. All right, so now a new idea here. What happens if we take those two capacitor plates and we connect them with some sort of material? What's going to happen? Is it that charge is going to flow through this material, whether it's a conductor or an insulator? Will charge flow through it if it's a conductor but not an insulator? The reverse of that, will charge flow through if it's an insulator but not a conductor? Or are we going to have no charge flow and the plates will remain fully charged? It turns out the best answer here is B, if that's a conducting material, a piece of copper wire, for example. Very quickly, the excess charge will flow. Again, in my head, I'm just going to have negatives move. Negatives are going to migrate back to the left-hand plate, making both plates ultimately neutral. But this wouldn't happen if it was an insulating material, because while an insulating material can store charge, charge doesn't move well on an insulator. And in fact, when we want to make a capacitor more effective, we put an insulating material in that region in the middle that has dielectric properties that increase the electric field, increase the ability to store electric charge, but don't allow charge to go from one plate to another. After all, if you do that, you no longer have a capacitor storing charge. So electric current, I would encourage you to frame your thinking by thinking about what you know about a more familiar current, a water current. So I may be going out on a limb here, but I'm assuming that everybody in their life has seen some form of water current, be it some sort of stream or river or creek or an ocean current, or if it's only as simple as you turn on a faucet and a stream of water comes out. All of those could be considered water currents, where water is moving from one place to another. When we talk about electric current, we're thinking about the same thing. Charges are moving from one place to another. And in fact, current is defined to be the amount of charge that's flowing from one point to another. What thing you can do is you could imagine you had some little counting device and you're just sitting by the side of a wire counting the number of charges that pass through per time. Just like when they do traffic surveys, they pay somebody to sit there by the side of the road and count how many cars go through a particular stretch of road in a given amount of time. So current has units of amperes, and 1 ampere is 1 coulomb of charge per 1 second of time. It also turns out, well, it's context dependent, but 1 ampere is a relatively large amount of current. You routinely have things in your house that are delivering more than 1 ampere of current to various devices, but 1 ampere of current going through you would be a very bad situation. Current also can be either direct or alternating. By those terms, we mean direct current implies that current is just going in one direction in an electric circuit, from a region of high electric potential to a region of low electric potential. In an alternating current circuit, the current is actually periodically switching back and forth. Here in this unit on electric circuits, we're just going to talk about the former, the direct current circuits, because it's easier to think about how they work. But we will, at the end of our electromagnetism unit, pick up some ideas about alternating current circuits. After all, AC circuits are the kinds of circuits that are powering your house, your room, wherever you're at, the circuits that are in my office here. And there are some distinct advantages to delivering power through alternating current, but for now we're just going to focus on direct current or DC circuits. So let's go back to our capacitor example here and up this a bit. So let's say I take my conducting material that I connected the plates with, cut it in half, and actually connect both of those halves to the two terminals on a light bulb. So that there is now a path connecting through a light bulb. What's going to happen? Nothing. The bulb's not going to light. The bulb light, but it will soon go out, or the bulb will light and remain lit. Turns out the best answer here is B, and we're making some assumptions here that we put enough charge on these plates to make it happen. But assuming that, the charges will actually flow. They'll flow through the bulb filament, The bulb filament is a conductive material, but it's a conductive material that when charges flow through there, it heats up, gets hot enough that it actually glows and gives off light. But this is the basis for how we light a light bulb. And the charge flows through the light bulb filament, lights the light bulb up. But because we started with a finite amount of charge on each of these plates, once the plates have returned to neutral, I no longer have any electric current flowing through the bulb, and the bulb itself goes out. But in that context, you actually can use a capacitor as a short-term storage device. In fact, many photographic flash units have capacitors built in so that when you open your shutter to take the picture, the flash flashes. A capacitor actually discharges through the light bulb, and then it is some period of time while that capacitor is recharging before you can flash the unit again. All right, now we want to think about some compare and contrast situations to help us build a model of what we mean by resistance. So let's say I go back to my original capacitor example and I connect the two sides of the capacitor with two wires that are the same diameter as each other, but they're made of different materials. One's silver and one is graphite, the same material you have in your pencil lead. What's going to happen? Does your intuition tell you that more charge will flow through the silver wire, more charge goes through the graphite wire, or the same amount of charge flows through both wires? If you said silver, you would be correct. All materials that are conductive, and both graphite and silver are conductive, have degrees of conductivity. And from the materials that we've explored, as far as people know, silver is the best material for conducting electricity and turns out heat. So if that's true, more charges will flow through the silver wire than the graphite wire. You can think about this in the context of like traffic flow. If you have two streets, one is paved, one is a dirt road, but otherwise they're equal length and equal width. In general, more traffic is going to go on the paved road because it's an easier path for that to drive on. All right, case number 2. What happens now if I have two wires that are made of the same material, silver, copper, what have you, but wire 1 is a small diameter wire and wire 2 is a large diameter wire? How do you think the flow of charges through those wires are going to compare? More charge is going to flow through wire 1, more charge is going to flow through wire 2, or more charge will flow through, or rather the same amount of charge flows through both wires. If your intuition tells you that more charge will flow through wire 2, you would be correct. When we study this, we do indeed get more current to go through a thicker wire. Again, I find this helpful to think about this in a traffic analogy, right? 1-lane road versus a 4-lane highway, you're going to get more traffic on the 4-lane highway per time than you will through that 1-lane road. Finally, what happens if we increase the distance? So in order to kind of visualize this, I put another negative plate over there on the right-hand side. And so my wire 1 stretches between my original two plates, but my wire 2 stretches a further distance to a plate that's equally positively charged but further away. What does your intuition here tell you about how the flow of charge through these wires compare? Will more charge flow through wire 1, more through wire 2, or the same amount of charge through both wires? Turns out in this case, more is going to go through wire 1 because it's shorter. And even though these are conductive materials, they do have a little bit of resistance to the flow of electricity. And so when the wire is longer, you have more overall resistance. Just like it's actually harder to push water through a 100-foot hose than it is to push it through a 10-foot hose. So more is going to flow through wire 1. And we can put all of these ideas about the individual parameters together into a single model for resistance. So if you increase the length of a wire, you make it more resistant, which is what we just said. We could write this as a mathematical statement as R is proportional to L, the length of the wire. If you increase, however, the cross-sectional area of a wire, you actually make it less resistance to flow. You make it more likely for charges to flow through there easily. And so resistance and area are inversely proportional to each other. We can say R is proportional to 1 over the area. And just as we've done in some of the modeling labs, you can combine those two proportionality statements into a single statement that says the resistance is proportional to the length of the wire divided by the area of the wire. And just like in all of the modeling labs, there is a constant of proportionality. This one, however, has physical meaning to it. So the constant that gets used here is rho, which is known as the resistivity, and it's the resistivity of the material, in the same kind of way that kappa, the dielectric constant, was the dielectric constant of the material you put in a capacitor. So again, rho, the lowercase rho here, is the resistivity of the material, and it is a number, and it actually has units of ohm. Let's see, it'd be ohm meters, and it characterizes whatever material it is that you're working with. So you can Google around and find tables online. It's also table 22.1 in our textbook. It gives you different materials. As you might expect, things like silver and copper have pretty low resistivities, so they don't make good resistors. They're good conductors. Whereas things like plastic and glass and wood have relatively high resistivities, and therefore if you make materials out of them, they produce large resistances to the flow of electric current. So I think one final question to think about our system here. If we have the capacitor that we've connected to bulb 1, which is the same situation we saw a few slides ago, and we compare and contrast that to an identical bulb 2, but bulb 2, instead of being connected to the capacitor, is connected to a battery. But the potential difference from one end of the battery to the other is the same as the potential difference from one capacitor plate to the other. What's going to happen in this situation? Both bulbs are going to light and stay on for about the same amount of time. Both bulbs light then go out, but bulb 1 stays lit longer. Both bulbs light and then go out, but bulb 2 stays lit longer. Or bulb 1 stays lights and then goes out, but bulb 2 stays lit. The best answer here, in my opinion, is D. Bulb 1 lights and then goes out when that capacitor is discharged and back to neutral. But bulb 2 will stay lit at least for some period of time. And absolutely, batteries eventually run out of the energy they store and quit pumping charge. But it's a much, much longer process than your typical capacitor. If you've used any flashlight in your life, you'll know that you have several hours to several days, depending on the type of bulb that's in that flashlight, before the batteries need to be replaced in that unit. So we are going to now be thinking about electric circuits that are powered by batteries or some power supply that we're going to assume has a continuous supply of energy to keep pushing charges through that circuit, unless we do something to the circuit that interrupts the flow in some other way. So when we connect a circuit, and a fairly simple circuit is shown here in the drawing, we have a battery, so some large dry cell in this case. And those batteries are always going to have a positive terminal and a negative terminal. The positive terminal is at a higher value of electric potential. The negative terminal is at a lower value of electric potential. And then this is shown wired to a resistor. So resistors that are used in electric circuits are typically made of carbon. And you can get resistors that have a wide variety of resistances. But this, shown on the left, is the simplest possible circuit. One power supply, one thing that resists the flow of current in that circuit. However, it's a pain to draw those pictures every time you want to talk about a circuit. And so folks have developed a way of drawing schematic diagrams or circuit diagrams that represent the same information, but are ultimately much easier to draw and also much easier to understand once you get some practice in thinking about circuit diagrams. So in this circuit diagram, the symbol for a battery is two parallel lines, but one is longer than the other, and the longer line is always on the positive side. Occasionally, you'll see a battery symbol as well, where it's long, short, long, short, long, short, long, short, and that pattern continues for several iterations as opposed to just a single pair. Notice point A and point B are labeled here on the circuit diagram the same as they are over here on my battery. And then to draw wires, you just draw straight lines. And so the lines are always horizontal or vertical in these circuit diagrams. And a symbol for a resistor, something that resists the flow of electrical current flowing through it, is just drawn as this little zigzag line that's in there. So this circuit diagram is identical in information to the diagram that is more realistic illustration over on the left. Well, what happens then if we think about moving through this circuit? What happens to the electric potential as we do so? So I'm actually going to start here at point B, so the negative terminal of the battery, or the negative side of the battery in the circuit diagram, and think about going through piece by piece in this circuit. Well, theoretically at least, if you do so, moving from B to A, you go through a battery, and that is an increase in the electric potential. If this battery is a D cell, for example, that's 1.5 volts. So that means every coulomb of charge that gets pumped through that battery increases in energy by 1.5 joules per coulomb. Moving from A to C, I'm moving through a wire. And wires, at least when we are doing theoretical circuits like this, we treat as pieces of the circuit that have no resistance. Turns out that's not exactly true. There's some small amount of resistance in copper or silver wires, and we'll talk about how that impacts this graph on the next slide. But if I treat AC as a free pass, no resistance there, it's just a perfect conductor, then there's no change in electric potential. There's no energy drop in those charges that are moving through the circuit when they go through that part of the circuit. I hit my resistor, and so I go through that resistor, and in that motion, those charges have to fight their way through that resistor, if you will. They transfer some amount of their energy to that resistor. If you were to actually feel that resistor, it's going to be warm, or if that resistor were a light bulb, right, it's going to be warm and glowing. So that is a place where energy is transferred from the charges to the resistor or to the light bulb, and the electric potential in the system drops. And in fact, it drops back down to whatever previous level it was, because D to B is another wire where the movement is quote unquote free in terms of energy, and the electric potential stays the same. This, by the way, is the model that I'm going to prefer and use for almost all the situations we're going to analyze in this unit. It's more realistic to do what's on the next slide, but it's also a more difficult model to use, because if I use the more realistic model, I have to do things like measure the length and the diameter of all the wires I use in my circuit so that I can determine how much resistance each of them have. It's a lot easier if you can just treat them as perfect conductors. And in truth, relative to the resistors and the things that we use in our circuit, they are pretty much that. But if we were going to be more realistic in here, we'd have the same thing. As you move through the battery, the electric potential would increase. It would not, in fact, increase by as much as it would in our theoretical model, because alongside going through the battery and through this chemical process which increases the potential energy of the charges, a battery itself has some internal resistance, some fight against this flow, some effects that are essentially taking some amount of that energy away. And so there's actually a less than full increase in electric potential. And as I go through those wires with small amounts of resistance, if I'm doing a realistic model, there's a small energy drop there, and there is a bigger energy drop going through the resistor, and then another small energy drop going the other wire back to the battery. So again, this is a more realistic model, but it is a harder model to think about, so we're going to prefer and generally use the theoretical one of the previous slide. How do all these parameters come together? Well, they come together in something known as Ohm's law. Ohm, at least the story I've heard, was a high school teacher in Germany and studying electric circuits in an era where a lot of things were being figured out about how electrical circuits behaved. And he figured out that these parameters were related in this way. So a battery is what provides the potential difference to the charges. Sometimes you'll see that called the electromotive force, or EMF. So charge gets pumped through the battery, and I like to think of the battery as a pump, just like a water pump pumps water. And then charge flows through the circuit as an electric current, and as it's moving through the circuit, it encounters resistance. So how are all those parameters connected? Well, Ohm's law is what details this relationship. So the stronger you make that pump, or the higher the potential difference of the battery, the more current you push through that circuit. You're giving charges more energy. More energy means more flow through the circuit. However, the more resistance you put in that circuit, that actually decreases the current. So current and resistance are inversely related, and you can pair them and say current is proportional to the potential difference divided by the resistance. As we showed in lab, you can work out what the proportionality constant is that makes that equals, not just proportional, and it turns out that is just 1, the number 1, and so from that we can say that current is potential difference divided by resistance, or I is delta V over R. That means if you know the potential difference of a given battery and you know the resistance that you have in the circuit, you can calculate how much current should flow through that circuit as a result. Ohm's law, by the way, also gives us a definition for and units for resistance. So resistance is the potential difference per current. So as charge flows through a resistor, however much of a drop that has in electric potential per 1 amp or 2 amp or whatever amount of current, that gives you how many ohms of resistance that resistor is considered to have. And 1 ohm, which is symbolized with the Greek capital omega, is 1 volt of electric potential difference per 1 amp of current. So we're going to wrap up this lecture by asking you to think about a ranking task related to resistance, but also voltage and current here. So the resistance and the magnitude of the current depend on the path that the current takes. So the drawing shows 3 situations in which the current takes different paths through a piece of material. So the piece of material is always 4 long, 2 wide, and 1 tall. But we either put the potential difference in scenario A so that the current flows through the full 4 length, or we put the battery, the potential difference in situation B so the current flows through the length of just L, or in situation C, the battery is hooked so that the current flows through the length of 2L. So how would these 3 blocks of material rank according to resistance? Well, if they're all the same material, they all have the same resistivity, so rho is the same. The one that's going to have the most resistance is the one that has the greatest length to flow through and the smallest cross-sectional area. And that is situation A, where you flow through a length of 4L, but the cross-sectional area is 2L times L. And the one that has the least resistance is going to be when you flow through that length of L, but the cross-sectional area of the material is 4L times 2L. And that means the resistance of A is going to be the greatest, resistance of B is the one that's in the middle, and C, with the shortest length and the greatest surface area, is going to be, or rather, C is the middle and B is the least resistive in these 3. So then how do they rank in terms of the amount of current that's flowing through those materials? Well, if B has the least resistance, B gets the most current. And similarly, if A has the most resistance, A is going to have the least current. Current and resistance are inversely related to each other when the potential difference is held the same. So that means the current is the highest through block B and the lowest through block A.